Good morning, everyone. Thank you very much for coming to our launch event. So my name is Sergiy Korposh. I'm Associate Professor at the University of Nottingham. And in this network, I'm co-I and leading a theme on remote sensing. So in this relatively short presentation, I will give a brief overview of existing sensor principles and technologies for remote blood testing. So I'd like to define what I think remote blood testing is, and in particular, two different approaches to how this can be achieved. Then I'll give a very brief introduction to principle of sensors that can be used to fulfill the main goal of remote blood testing, and show two brief examples of multiparameter measurements that I found in literature, one in literature and one from our lab, that I think can be used in future to expand to some biomarkers detection and for remote blood testing. And finally, just to summarize what Vicky already introduced in her presentation, so what is the main goal of our network and what we would like to achieve at the end of three years. So remote blood test, the blood sensing. So what do we see as remote? We can divide it into two main approaches. I think it's one is invasive, where we collect blood samples remotely and then send them to the lab. And I think this is currently what is happening in clinical practice when we talk about remote blood sensing. And the second approach, where we have point of care devices and remote analysis is happening in so sample collection and analysis is happening at home or remote location, and then results are sent to clinicians for providing diagnosis or processing information. And this different point of care devices can be implantable, for example, or the current sensors that I use, for example, glucose monitoring blood, like finger prick sensors. So just two examples. I think the other approach, and is probably where we're talking to a very remote future probably here, but is if we can achieve all of this, but non-invasively or minimally, using minimally invasive technologies. So for example, detection of biomarkers in other samples, so indirect blood analysis, using samples such as breath, saliva, urine, or sweat. And I show one of the examples today from in literature where biomarkers can be measured in sweat, for example, and provide indirect information about blood content or blood chemical parameters that we want to detect. The other approach is non-invasive remote analysis using spectroscopy or wearable sensors. And this, we have examples of blood pressure measurements or heart rate measurements using certain smartwatches or wearable technologies that enable us to obtain this information. But these are mainly about blood pressure, heart rate, rather than about chemical composition. Recent advances in science and in technology, such as Raman and terahertz spectroscopies, might open the opportunity to conduct chemical analysis remotely as well. And I'll explain very briefly how these different technologies work in my next presentation. I think Mark and Rob will explain more how wearable sensors can be used in obtaining useful information. So a very brief introduction to different sensing principles. I will start with electrochemical sensors, as this is the main principle behind glucose sensor, for example. And the different types of them, but the main principle behind is very similar. So you have a sensing working electrode, you have a counter electrode, and have a reference electrode. The whole clever bit, sensing bit, is happening at this working electrode, and where exchange of electrons or reduction, oxidation is happening at the surface of this working electrode. Selectivity typically is achieved by using this diffusion barrier or ion selective membrane. So certain ions will diffuse inside the electrolyte, and you will measure the current or voltage change depending on concentration of the presence of different ions in this electrolyte. So typical sensogram that you obtain shown in here. So this is voltammogram, where depending on whether you increase potential difference across electrodes or decrease it, so you'll obtain a different physical interaction at the surface of the electrode. And by measuring the amplitude of the current or location of the peak or voltage at which this happens, you can tell what ions are present there and how much of these ions are present there. There's a second type of the sensors that I wanted to discuss today is so-called mass-sensitive devices. So this can be based on surface acoustic waves or bulk acoustic waves. And the typical example of this is quartz crystal microbalance. So what is happening? You have a crystal, a thin sheet of crystal typically, and by applying various frequencies to it, you oscillate it, and depending on the mass adsorbed on the surface of this crystal, you will see a different frequency response. And again, by measuring this frequency change, you can tell how much of this material has been absorbed on the surface of the material, so you can provide the quantitative information. And the last two technologies I wanted very briefly to discuss, optical waveguides, so optical fibers, and this is my main research area. And these optical waveguides can be used to detect heart rate, so they can be simply used as a waveguides to deliver light to the measurement zone. So this is, for example, optical fiber integrated into a sock. And this is one of the projects we're working in our lab that enables you to develop a variable sensor that can measure heart rate, potentially blood pressure as well. And we're working now on some chemical sensors as well. And this is mainly for measuring diabetic foot ulcers. So you can incorporate sensors inside the socks or wound dressing and measure certain parameters. The principle behind this is that you have a waveguide, so typically just thin glass. You launch light into it, and then this light will measure the propagation of the light inside the glass will change with a change of analyte concentration adsorbed or interacted with optical fiber. And the final technology, a so-called spectroscopy, so Raman and terahertz spectroscopy. And the principle behind this is relatively simple. So you have a light source, you shine this light source at the tissue or sample you would like to measure, and then you collected the scattered light. And this scattered light, depending on chemical composition of the tissue or sample that you have in there, you will see the scattered light at different wavelengths. And this provides like fingerprint information, so different compounds, for example, shown in here, ethanol and methanol, although very similar in chemical structures, they will show very different fingerprints, and you can determine then what compound is present there. By measuring the intensity of the reflected wave, you can tell how much of this material is present inside the sample. The real difficulty with this is that signals that you're measuring, reflected signals or scattered signals, are extremely small, so it still requires a very bulk equipment to be able to conduct sensitive measurements and reliable measurements. So with all sensors that I have introduced, transducers, they're typically not selectively sensitive, except the last one, which is spectroscopy, which can provide qualitative information about a sample. The other sensors, they will require a certain capture layer or sensitive element that can selectively interact with analytes we would like to detect. And then they provide a certain change in the signal. So this, for electrochemical sensors I showed, this can be current. For optical sensors, this will be change in refractive index, for example. So these sensitive layers will be interfaced with a transducer, with material, and provide selective response. So we can then determine quantitatively and qualitatively what's present inside the complex sample. Because one of the biggest challenges with any biosensor, chemical sensor development is its selectivity, and blood is extremely complex medium in which if we would like to detect a single analyte, will be quite difficult to achieve. So going to examples of blood measurements, and it's one of the interesting papers recently published by Wong's group in San Diego, University of California. So they proposed the epidermal patch for blood analysis, and this is a picture of this flexible polymer that consists of several electrodes, And this patch can provide information about blood pressure. It can also measure some chemical concentration of chemical compounds, such as glucose, alcohol, lactate, and caffeine. The principle, how it works, so they send for blood pressure, they have ultrasound sensors there, so they're sending wave into the into capillary, and then they measure when the pulses travel, and a distance between pulses can tell you the time that passes between two different pulses can provide information about blood pressure. So you can also use this for heart rate measurements, and also, so as I mentioned, so some sweat biomarkers that are detecting. So this is a nice example of multi-parameter measurements, and this, I think, where sensor technology will need to excel if you would like to provide a remote information about blood concentration. So it's ability to measure several parameters at the same time. And a second example I wanted to show today is from our group, where we have developed optical fiber sensor to measure anti-cancer drug in vivo. So the idea is to detect dabrafenib, that is targeted anti-cancer drugs, and the main problem with it, it's very successful in treatment of certain types of cancers, but there is some patients will develop a resistance, and it's major cause of concern, and it leads to treatment failure and poor patient outcomes. So ideally, what we'd like to provide clinicians with is a tool that will provide information about the early resistance, so to measure biomarkers, but also where the patient is receiving the therapeutic dose of a drug. And in this project, we have addressed one of the concerns, so we, in particular, detection of dabrafenib. So I'll show a couple of slides of how this was achieved. But as I mentioned already, the ultimate goal is to have a multi-parameter sensor systems where we have sensor elements across the optical fiber, modified with particular sensitive layers that will enable us to measure the dabrafenib concentration of a drug, but also biomarkers such as cytokines that will enable us to tell whether there is resistance developed or not. For the sensitive layers, we're using molecular imprinting approach, where our analyte dabrafenib is used as a template, and around this template we're creating the polymer matrix. And this matrix will bind chemically to the analyte, and once we have removed this analyte, we can create a cavity that will mimic chemical and physical properties of the target molecule we would like to measure. So this provides extremely high selectivity and also high sensitivity combined with our transducer. So we would like to test this for validation in 3D cancer spheroid models. We haven't achieved this yet, so I'll show you the first step towards this direction. So this is a structure of the sensor. So we have an optical fiber, which consists of the core and a cladding. We inscribe a grating element here, and when light propagates inside this optical fiber, because of the grating, it will scatter and propagate inside the cladding. So any change now in external medium will lead to the change of light propagation inside the optical fiber, and we can measure this. So then we have coated optical fiber with this molecularly imprinted material. So we use a dabrafenib as a target compound here, and we also tested it across different structurally similar compounds, so to prove that we have a selectivity. And signal we're measuring is the wavelength shift here, so you can see this band shown here is because of the grating presence, and when we modify fiber, you can see how the signal changes, and we can obtain we can obtain the concentration dependence with dabrafenib when we expose it to dabrafenib, so we can measure concentration of dabrafenib in a sample. So if you want to see more details, so this is a paper we have published recently. And the final approach I just want to discuss is for non-invasive analysis of biomarkers. So it is known that certain compounds exhaled from breath or from sweat or present in urine can be used as indicators of blood composition, of blood chemical composition as well. So for example, for diabetes, so glucose level in blood, we know if that increases, acetone exhale from breath increases as well. And this creates a prospect for measurement of the analyze and determining non-invasively the blood composition. So what is the main goal? So we can shown already this slide. I just added a last sentence. I won't be repeating all of this. So the main goal of this part of remote monitoring in our network is to identify a technology gap, bridging of which will enable real-time remote multi-parameter blood testing. And I hope in 3 years we'll identify these gaps and we'll be able to provide a direction towards bridging this gap. So and some interesting projects that will enable to achieve as this main goal. So this is just a slide for as Vicky has shown already. Thank you very much for your attention. I'm looking forward to any questions and discussion and working together on this exciting network. Thank you.